Hello everyone, welcome back to SWEC Talks. I am Uma from 2nd CSC and my teammate Sri Ramya had made this presentation under the guidance of Dr. M. Prasad Sir, Associate Professor, Department of CSC, SWEC Bhimavaram. Today, we are going to dive into the topic Storage and I/O structure. Let's get started. Storage structure in operating systems. Basically, we want the programs and data to reside in main memory permanently. Now, what's main memory? Main memory, often referred to as RAM, random access memory, is the fast volatile storage where our computer's programs and data are temporarily stored while it's powered on. However, there are two significant challenges when it comes to making main memory a permanent storage solution. The first challenge is the size of the main memory. Despite being fast and efficient, it's usually too small to accommodate all the programs and data we need permanently. Imagine trying to fit an entire library into a single room. It's just not feasible. As technology advances, the size of main memory has increased, but it still falls short of providing permanent storage for all our computing needs. The second challenge is the volatility of main memory. Unlike secondary storage devices like hard drives or SSDs, main memory loses its contents when the power is turned off. This means that any data or program stored in RAM disappear when you shut down your computer. This volatile nature makes main memory unsuitable for long-term storage, and we need alternative solution for retaining data beyond power cycles. Now that we have understood these challenges, let's explore why these limitations exist and how computer systems address them. Main memory is designed to be fast and provide quick access to data, but this comes at the cost of limited storage capacity. Larger memory sizes would be smaller and more expensive. As a result, a balance is struck and main memory is optimized for speed rather than permanence. To overcome the limitation of main memory, we use secondary storage devices. There are two types of storage devices. First on our list is volatile storage, also known as primary storage. This is the swift and responsive memory that works hand in hand with your computer's active processes. However, it has a unique characteristic. It loses its contents the moment the power is removed. It's like a clean slate, always ready for the next task. Next up, we have non-volatile storage, our secondary storage hero. Think of this as a reliable archive for your data. Unlike its volatile counterpart, non-volatile storage doesn't lose its contents when the power is removed. It's the digital vault that securely holds all your information, ensuring nothing is lost in the event of a power outage. Now we are diving deep into the heart of computing, primary memory. This integral component is like the backstage VIP access for our processors. Let's explore the significance and functionalities of primary memory together. At the core of a computer's operation lies primary memory, the initial port of call for a processor. It's the direct gateway allowing our machines to access programs and services actively in use. You might hear it referred to as primary storage or main memory. These terms are interchangeable, describing the critical space where the magic happens. Primary memory is the epitome of volatile storage in a computer system. Even though there are components like data buses and cache memory, the most common example that comes to mind is random access memory or RAM. It's like the short-term memory for our devices holding information temporarily for quick accesses. Now that we have understood the dynamic nature of primary memory, let's delve into its role in loading and executing essential components. As soon as you power up your computer, the OS user interface and any user installed software utilizes perform a grand entrance, all loaded into main memory. This is where the action begins. When you launch a program or application, it engages with the system processor, utilizing the resources available in main memory to carry out its unique functions. It's worth noting that while primary memory is the speedster in this digital realm, secondary memory plays the role of the reliable workhorse. Secondary memory like hard drives or SSDs is considered slower in comparison. Primary memory is optimized for quick accesses and swift interactions, making it the go-to choice for actively used programs. Let's shine a spotlight on an unsung hero in the realm of computing, secondary memory. This non-volatile powerhouse plays a crucial role in sharpening our digital experiences. Now, at the core of permanent computer memory lies secondary memory, a non-volatility, steadfast companion that doesn't dance in the limelight. Unlike primary memory, it's not directly accessible by the computer or processor. Instead, it quietly stores data for the long term, providing a sanctuary for information that doesn't need to be in the immediate spotlight. You might hear the term secondary storage, and that's just another way of referring to a steadfast friend, secondary memory. It goes by many names but plays the same crucial role in the grand symphony of computing. Now, let's explore the cast of characters in the world of secondary memory and understand its unique features. Secondary memory boasts an impressive lineup: read-only memory, flash drives, hard disk drives, magnetic tapes, and a variety of internal and external storage media. These significant guardians patiently hold vast amount of data ready to be summoned into action when needed. Unlike the speedy hare that is primary memory, secondary memory is more like the steady tortoise. It might be slower in accessing and retrieving data, but what it lacks in speed, it makes up for in endurance. Even when the computer is powered off, data rests peacefully in secondary memory, patiently waiting for its moment to shine. One of the standout features of secondary memory is its colossal storage capacity. From a few megabytes to multiple terabytes, secondary memory can store vast amounts of data, making it a to-go solution for our ever-expanding digital needs. Since we have understood about primary and secondary memory, let's see the differences between both of them. Primary memory is also primarily known as main memory or primary storage memory. Secondary memory is also primarily known as secondary memory storage. Primary memory is also known as internal memory. Secondary memory are also known as auxiliary memory or backup memory or additional memory. Primary memory is more costlier than secondary memory. Secondary memory is less costlier than primary memory. Primary memory is said to be faster than secondary memory. Secondary memory is said to be slower than primary memory. Primary memory stores the information or data that the processing unit is currently using. Usually, capacity ranges from 16 gigabytes to 32 gigabytes. Secondary memory has a substantial amount of information and data storage. Typically, capacity ranges from 200 GB to terabytes. Primary memory can be divided into volatile and non-volatile memories. Secondary memory can be only classified as non-volatile memory.
Computing, understanding the hierarchy of storage devices is crucial. This hierarchy represents a continuum of storage options with each level balancing performance and cost considerations. Additionally, a fundamental distinction exists between volatile and non-volatile storage. Now I tell the parameters. First one is high performance and high cost. At the time of the hierarchy, we encounter storage solutions renowned for their exceptional speed and responsiveness. Electronic disks situated at the pinnacle are shift efficient but often come with a high price tag. Next one is cost versus access time. As we descend through the hierarchy, we observe a recurring pattern. Cost per bit tend to decrease, which can be economically advantageous. However, this reduction in cost is typically accompanied by an increase in access time. Is akin to trading speed for affordability as the storage devices become more cost effective. Next one is volatile versus non-volatile. An essential differentiation lies in the volatility of storage devices. These located above electronic disk in the hierarchy are considered volatile. These devices, when power is interrupted, lose their data. Conversely, the storage devices below electronic disks are categorized as non-volatile. They maintain data integrity even in the absence of power. making them suitable for long-term data storage. We are going to explore a critical aspect of I/O processing in computers, I/O interrupts. This concept is a game changer when it comes to efficient data transfer and multitasking. So let's dive right in. To understand I/O interrupts, let's use a practical example. Imagine you are sending a document to your printer. In the world of I/O interrupts, this interaction between your computer and the printer is an excellent illustration. First one is CPU register loading. When you decide to print a document, the CPU does not directly send data to the printer. Instead, it loads data and control information into registers within the device controller. These registers tell the device controller what operation to perform. It's like telling the printer what exactly you want it to print. Next step is synchronous I/O. Now there are two possibilities when it comes to I/O operations: synchronous I/O and asynchronous I/O. Let's start with synchronous I/O. In this case, after the I/O operation is initiated, the control is held by the CPU until the operation is completed. It's like you waiting for the printer to finish printing before you can do anything else. Next one is synchronous I/O. Think of it as you standing by the printer, ensuring the document is printed correctly before you move on to your next task. Next one is asynchronous I/O. Now let's talk about asynchronous I/O. This is where things get interesting. In asynchronous I/O, the CPU does not wait for the operation to finish. It hands control back to the user process immediately. It's like sending a print job and then being able to continue working on your computer without waiting for the printer. Next one is asynchronous I/O. Imagine you hit print and without hesitation you can go back to your work on the computer. The I/O process and the user process run simultaneously like two parallel tasks. While we are going to delve into a fundamental aspect of input or output processing in computer systems, programmed I/O is a simple yet essential concept that plays a key role in how data is transferred between the CPU and external devices. Let's begin by visualizing how programmed I/O works. Imagine you are sitting at your computer typing a document using your keyboard in the world of programmed I/O. This interaction between you and the computer is a great example. When we talk about program I/O, we mean that when you type something on your keyboard, the computer expects the keyboard to be ready to receive that input. In other words, it's like you telling the computer, I am ready to type, are you ready to listen? Next, the waiting phase. If the keyboard is not ready because it's still processing a previous input, your computer has to wait patiently. It's just like you waiting for your turn at a busy ticket counter. Next one is checking output buffer. Now let's talk about the other end of the process. After your input is accepted, your computer needs to check if the output device or output buffer is free to handle the data. This is crucial, just like a printer checking if it has enough paper to print your document. Next one is a continuous process. This back and forth process of waiting for the input device to be ready, providing input and checking if the output device is available continuous every time you transfer data. It's like a well choreographed dance between your computer and its peripherals. We are going to explore a critical aspect of I/O processing in computers, I/O interrupts. This concept is a game changer when it comes to efficient data transfer and multitasking. So let's dive right in. To understand I/O interrupts, let's use a practical example. Imagine you are sending a document to your printer. In the world of I/O interrupts, this interaction between your computer and the printer is an excellent illustration. First one is CPU register loading. When you decide to print a document, the CPU does not directly send data to the printer. Instead, it loads data and control information into registers within the device controller. These registers tell the device controller what operation to perform. It's like telling the printer what exactly you want it to print. Next step is synchronous I/O. Now there are two possibilities when it comes to I/O operations: synchronous I/O and asynchronous I/O. Let's start with synchronous I/O. In this case, after the I/O operation is initiated, the control is held by the CPU until the operation is completed. It's like you waiting for the printer to finish printing before you can do anything else. Next one is synchronous I/O. Think of it as you standing by the printer, ensuring the document is printed correctly before you move on to your next task. Next one is asynchronous I/O. Now let's talk about asynchronous I/O. This is where things get interesting. In asynchronous I/O, the CPU does not wait for the operation to finish. It hands control back to the user process immediately. It's like sending a print job and then being able to continue working on your computer without waiting for the printer. Next one is asynchronous I/O. Imagine you hit print and without hesitation you can go back to your work on the computer. The I/O process and the user process run simultaneously like two parallel tasks. Now we are going to the last topic of today's presentation. We are going to explore a fascinating concept in the world of computer systems: direct memory access, or DMA. This method has a significant impact on enhancing the speed and efficiency of data transfer. Let's jump right in. First, imagine you are working on your computer, transferring a large file from a storage device. This scenario is a perfect example to understand DMA, where the device controller directly communicates with memory without knowing the CPU. First step is device controller setup. So how does DMA work? First, the device controller is responsible for configuring the necessary resources such as buffers, pointers and counters. Think of this as the device controller setting the stage for the data transfer. Next one is data transfer. Once the stage is set, the device controller takes over, transferring blocks of data directly to memory without needing the CPU to step in. It's like having a skilled courier who takes your package from one place to another without bothering you. Next step is high-speed I/O. DMA shines in scenarios where high-speed I/O devices are involved. These are devices that can transfer data rapidly, and the CPU would otherwise become a bottleneck in managing the data flow.
We hope this video clarifies the above all topics. Thanks for joining us today.